Hi, everybody. Today we're going to be discussing something that's more related to sound waves that you deal with on a more regular basis, which would be intensity and decibel level. You've heard of the decibel level, and you'll be happy to know it's something that's logarithmic. Everybody loves dealing with logs, right? Anyway, for conversation's sake, say you increase the power level going to your speakers. You know that the intensity of the sound that you hear will obviously increase. There's some kind of relationship, direct or squared or something like that. But as you have more power, the intensity on your ear will increase. You also know that as you get farther from the source of the sound, the intensity on your ear will decrease. And one thing you may not know is that, yeah, we've been studying waves, sort of, and sound, definitely. But when you make a sound, it's not just a two-dimensional wave. When you make a sound, anyone near you, above, below, or to the side, can hear you. That's because it doesn't go out in a two-dimensional wave, but that wave goes out in a three-dimensional wave. It's actually the surface area of a sphere. It's the spherical wavefront that goes out. So we got to put all these ideas together to create an expression for the intensity of a wave. Or I'm sorry, the intensity of the sound that you will hear. So putting what we just said together, the intensity I is directly related to the power. More power, the more intense it'll be on your ear. You also know that as you get farther away, the sound will decrease. So we know how to put distance in the denominator, but as I mentioned, this is a spherical wave. So its energy is dissipated over the surface area of a sphere, which is 4 pi squared. So this is a basic expression that relates intensity and the power used to make that sound. So power is measured in watts, just so we have this straight. P is power measured in watts. Sorry. R is distance from that source. So the distance from the source of the sound, and it's measured in meters. So if you wanted to get the units for intensity, I know I has been current in the past, but I don't know, now it's intensity. You'll have to live. And if you just look at our expression, we have power, that's watts in the numerator, and we have, where did my R go? Should be pi r squared. I'm sorry about that. I thought I wrote an R, maybe I didn't. But back to the point is that it's R squared. So that's meters squared. So the units for intensity are the amount of watts per meter squared. Yeah, interesting. All right. So that's a basic expression that relates power and intensity that you hear based on distance. But then there's an expression for the decibel level, which is logarithmic. So bear with it. It's really not a big deal. I know when we're in class, I usually get moans and groans about logs, but get over it. It's actually really easy. So this is the expression. There's no deriving it. There's no discussion, but this is the expression that relates decibel level to the intensity. The intensity is what we hear in our ear, and that'll give us a decibel level. So dB stands for decibels, decibels. I is intensity, we know that already. But I sub naught. I naught is the threshold of hearing. Anything less than that, any less than this intensity, we cannot hear. There's also a threshold of pain. There's an intensity for that, and anything more than that, and we start to feel discomfort in our ears. So this is the threshold of hearing. And it's a constant, it's just a number value. It's 1 times 10 to the negative 12 watts per meter squared. So this is the math associated with what we're going to be discussing and the variables and what they stand for. And we're going to do a little samplage. So if you haven't got this all down, you may want to pause the video because I'm moving on. Normally we'd be in class and I would ask someone to scream as loud as they can. I like to see if people down the hallway come out to see if anything happened. But somebody usually volunteers. And if you wanted, you could download an app on your phone where you can measure decibel level. I do that for the classroom, and I've done it for a noisy neighbor who's 3 doors down or 3 houses down, who at even, I'd guess, 200 yards away, still was blasting out nearly 90 decibels at 10 o'clock at night. I'm an old man. It bothered me. I called the cops. I miss telling stories, apparently. Anyway, so what we're going to do is, I hate to say use last year's example, but if you want, download that app and start measuring decibel levels. Should be interesting. So last year we had somebody scream, and they registered a decibel level of 95.5 decibels. And I was located a distance of 4 meters away. So 95.5 decibels at 4 meters away. And we wanted to figure out what was the power of this shout. All right. So we have a decibel. We're going to use our new decibel expression. Seriously, just subbing it in. 95.5 decibels equals 10 log of intensity over I naught, which is the threshold of hearing, which is 1 times 10 to the negative 12 watts per meter squared. So order of operations here is kind of important. And the first thing you're going to want to do is divide both sides by 10. That's all. That's your first step. That's all you can do. And you get 9.55 equals the log of I over I naught. All right. I know the math teachers would be upset with me, probably, if I said this, but you got to get rid of that log. Inverse log is not the right thing to say. I know that. But basically, take both sides and put them to the 10 to that power. If you know what I'm talking about, people have done logs before. But basically, on your calculator, you're going to hit second, and then you're going to hit log, and it should look like second log. So you should get something that looks like 10 to the 9.55 on your calculator. That's what it should look like on your calculator. When you do this, you're gonna get a big number. That's all I can say. A big number. And that will equal I over I naught. From here, it's pretty straightforward, but I want to highlight this one more time. This is that step. To get rid of the log, you put both sides 10 to that power, 10 to the 9.55, and 10 to the log of I over I naught just becomes I over I naught. Solving for I. We get an intensity. It's not a lot, 0.00355 watts per meter squared. That's our intensity. We can now use that and our new expression, our other mathematical expression, to get the power, because we know that the intensity is power over 4 pi r squared. So there's our intensity, watts per meter squared, is equal to the power over 4 pi r squared. Our distance is 4 meters. So very common mistake here is forgetting to square the 4. Don't forget to square the 4. And if you do it properly, you should get a power output of 0.71 watts. Not a lot of power. Not even enough to light a light bulb. But it was a loud shout. Trust me, it was loud. The person who shouted last year. Speaking of this expression right here, just going to sneak this in over here. I equals P over 4 pi r squared. This time I didn't forget the r. Please be careful. Very common mistake here. When you're putting things in your calculator, there's a difference between, for example, 5 divided by 4 pi times 3 squared. You do that, that's completely different than 5 divided by 4 pi 3 squared with the whole thing enclosed in parentheses. So you're going to want to put the denominator in parentheses, please. Otherwise, you're multiplying by, or you're dividing by 4, and then you're multiplying by pi times 3 squared versus dividing by 4 pi times 3 squared, the whole quantity. So please watch order of operations on that. All right. The next thing we could do, always entertaining in the classroom, is have the rest of the class scream as loud as they can. And then we assume that everybody screams with the same power level. Okay, so let's talk about that. It's maybe like if 19 people scream with the same power, sorry, handwriting not good, same power as the person who originally screamed. Person who originally screamed. Who originally screamed? So we want to know what will be the new decibel level. I'll tell you this, you don't multiply 95.5 times 19 decibels. If you do that, you're somewhere in what, the 1,900 decibels. I'm pretty sure at that level, your body would just be obliterated. It's a really loud sound. I don't even know what that would look like. So it's not a multiplication thing. But when you see a question like this where it says, what would your new decibel level be? It's asking you to compare what happens if there's 19 people making a noise versus 1. All right. So what we're going to do when you see this question, you want to use a ratio of I to I naught. Think of this as your new intensity versus your old intensity. Don't think of it as 1 times 10 to the negative 12. All right. So if we have 19 people screaming, then that's 19 times the power up here, which would be 19 times the intensity. So if we put that into math, you end up with a decibel level equals 10 log, take a ratio of your new intensity, 19, compared to your old. Your new to old is 19 to 1. Again, 19 people screaming with the same power gives you 19 times the intensity. Simply putting this in a calculator, you would just do 10 log of 19, and the calculator would spit out that it is 12.78 decibels. That's not the new decibel level. That's how many more decibels you would get with 19 people screaming. So this is 12.78 decimals more. So if we add it to our original of 95.5 decibels, we get a new decibel level of 108.28 decibels. So those are two examples using the new math. The first one I want to bring to your attention that we took our way all the way through the math. We had a decibel level. We used that decibel level to get an intensity. Once we got the intensity, we were able to find out our power. We can go the other way. You could be given a power and a distance and use that to get an intensity. And then from the intensity, you could get a decibel level. So we can go in that direction. The second problem we did here, this was, again, it's a comparison. I want to make that really clear. You'll see problems like if 10,000 things happen instead of just 1, what's the new decibel level? Well, here it's 19 instead of 1. You see this, the 19 versus 1, or whatever the homework says, 100 versus 1, or 50,000 dogs bark instead of 1. Just do a ratio of the new to old number of things making that noise. And you'll get a new decibel level. You get how many more decibels, and you add it to the original. All right. There's one more thing we have to do. We have to look at a funky, funky chart. So here we go with that. Here's that funky chart I was talking about. You have this exact chart at the top of your homework. It looks intimidating because it's got decibel levels on the left, it's got frequency along the bottom, and then it's got something called fons on the right. Now, fon is a unit of loudness. That's all you have to think of it as. It's a unit of loudness. It's how we perceive the sound. It sounds this loud to us. So here's how this graph is weird. Everything on this line that I'm highlighting here, let me get that thicker, that might work better. Everything along this same line, God, I can't even trace lines, sounds the same to us. It has a sound, and it sounds like 80 fons. So what does that mean? It's a little weird. Let's use this one as an example. Let's take the 30 fon line, because that'll be very drastic. So here's our 30 fon line that I am tracing. So what does this really mean? All right, well, let's take an example. I'll go with some green here. If I look at the 30 fon line, I go to 1,000 hertz. Here's 1,000 hertz, and I go up, and I put a dot. That goes over and hits 30 decibels. So 1,000 hertz at 30 decibels. That's what we're hearing. That's a 30 fon hearing. I'm going to trace this line, the blue line, up. I'm going to go over to actually 80 hertz. So here's 80 hertz, and I go up, make a dot, and move over. So what does this mean? Now we're at 60 decibels. Are we hearing 60 decibels? No, we're not hearing 60 decibels. We're hearing 30 fons. Again, this is what it sounds like to us. But what you need to see is that to hear 80 hertz the same way we hear 1,000 hertz. So I'm going to write that out here. 80 hertz sounds the same as 1,000 hertz at 30 fons. We need to crank up that decibel level. That's what it's saying, because at 1,000 hertz, it was only 30 decibels. Remember, that relates back to intensity, which relates back to power to create that sound. But 80 decibels, if we want to hear that, we have to crank that puppy up to 60 decibels. Okay? And remember, decibels relates to intensity, which relates to power. So is it twice the power if we've doubled the decibel level? Please say no. It is not. So we're going to figure out how many more or how much more power is actually required to make that sound. But what you got to take away from this is if you look at the trend of the graph, as we get to the lower frequencies over here, the decibel level required to make that sound, remember that relates back to the power, goes up. So what does that mean? It means we don't hear low frequencies very well. We need to crank up that decibel level, the power, so that we can hear it. And then somewhere here requires the least amount of decibels to hear, and then it starts going back up again. So when we get into frequencies into the 15,000, 16,000, we got to crank it back up, the decibel level. But we really apparently have trouble hearing some lower frequencies at low sound volumes. So we have to figure out how much more power was required to hear this 80 hertz at 60 decibels than 1,000 hertz at 30 decibels. The difference in decibel level between the 80 hertz and the 1000 hertz is 30. So how much more power is required for this? Let's find out. Wow, that jumped around a little bit there. So the 30 extra, I'm just using my decibel equation, 30 decibels. Now this is a comparison. So I'm going to use the I over I naught. I'm not using the 1 times 10 to the negative 12. Only use that if you're doing calculations. If it's a comparison, you do I over I naught. So that's 10 log new intensity as related to old intensity. And when you do this, you get that I over I naught is 1,000 times more intense, which also means, because there's a direct relationship to power, you need 1,000 times more power. That's nuts. So if the point of this thing is to tell you that if we want to hear 80 hertz, the same intensity on our ear, the same way we hear it, I shouldn't say intensity, the same way it sounds to us on our ears as we hear 1,000 hertz, you have to crank up that volume, like the power, 1,000 times, because we just don't hear lower frequencies as well. So this has been some examples with the math and also how to read the graph, which is a little intimidating. And there's actually only one assignment associated with this, and that's it for this week. And then there's the other assignment with you creating the video, which I'm looking forward to editing together. But as always, work with other people, work with me, send me an email, stop by for office hours if you have any trouble with the math. That's it. So I hope you're doing okay. I hope you had a good weekend, and stop by if you need me.